Let's talk about eCAVs. Not sure what eCAVs are? Want a hint? They are not, in fact, electric cattle. No, but they are in that general realm. Yes, my friends, we're talking about electric commercial agricultural vehicles. The agricultural sector is moving toward electrification these days. Why? Well, there is a global push for sustainable farming. There are stricter emissions regulations. And that doesn't even scratch the surface when it comes to the rising costs of traditional diesel machinery. But what does that mean to you as an engineer? Well, to keep pace with this electrification, we are now facing new challenges in powertrain design, thermal management, sensor integration, and more. And how can you get a jump start on the next generation of eCAV designs? With this here Chalk Talk. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Youssef Bouguerba from onsemi and I explore the eCAV landscape, break down the core architecture that distinguishes these vehicles from standard EVs, and check out how onsemi's portfolio of power modules, image sensors, and connectivity solutions can help you optimize your next eCAV design. And before we get started, don't forget to click that link. There you can find even more information about this topic from onsemi. Hi, Youssef. Thank you so much for joining me.
Hi, thanks for inviting me.
Absolutely. Okay, so first up, Youssef, what exactly is an eCAV and why is this sector booming right now?
Yes, good question. So eCAV stands for Electric Commercial Agricultural Vehicle, as you see. So these are commercial farming machines, usually powered by diesel gasoline engines today, but now transitioning to battery electric and hybrid electric. So you can imagine in a field, an agricultural field, it could be a spraying machine, a harvesting machine, a tractor, a sowing, fertilizing machine. So these, once they are becoming electric, that's what the E stands for, they will have, of course, the battery, which is the hard component of these machines that needs to be managed. So by a BMS system, as you see in this diagram here, then you need to charge it externally. Then you need an onboard charger to convert the energy. You need, of course, the second key component, which is the electric motor that needs to be driven by a traction inverter. Then you have some auxiliary things as well, like machine vision, hydraulic systems that could be also electric, and so on.
Youssef, what makes an eCAV different from a standard EV, and what does its core architecture look like?
From battery point of view, it should be like the same. So there is a 400-volt battery, as you see here on this block diagram, with more components, or 800-volt. This is the new voltage levels that is trend going to in the future. But the power levels will be different from a basic electric vehicle. So we have heavier machines here. They have also some auxiliary systems. So looking at the picture here again on the battery, this battery has to be charged. So you see you need some components in the OBC, it stands for the onboard charger. On the top right, you will see the electric motor that is driven by an inverter. It could be a three-phase or multi-phase inverter. This inverter is powered by the battery. So it's converting the DC energy to a AC voltage by the inverter, where the components from onsemi come into place, looking at here like silicon carbide, IGBT, JFET, and so on. The intelligence or the brain of this is the main controller you see in the middle. The controller has some memory, some clocking, and some switches. It needs a gate driver to access to the switches, the semiconductor switches. But then on the bottom, you will see a range of functionalities or auxiliaries. So starting from the vision system, that you need image sensors to capture the field, to do some sensing of or using a radar or a LiDAR, ultrasonic sensors. So all kinds of sensing elements to capture the field and make decisions based on this information. Then you have a communication, you have some smaller motors, usually replacing the hydraulic systems, these motors that do the harvesting, the fertilizing, all kinds of activities and mechanisms that you need to do on the field. Then it has a light, of course, so you need to light in the night or during the day. So you need LED drivers to light control these elements. And then if you see on the bottom left, they will be still finding the 24-volt battery or the 48-volt battery, so the standard low voltage battery, that some systems will still be working on that. And then you need to convert these voltage levels to a higher or lower levels to operate all these subsystems. So in total, let's say the power levels are different from electric vehicles, but also these kind of hydraulic systems as well, you would not find the same in electric vehicles because these machines are heavier, are doing other activities than a normal passenger car. But at the end, so the battery voltage would be the same for 100-volt battery, but also transitioning to 800-volt for higher power levels.
Youssef, beyond tractors, what vehicle types are being electrified and what are the top energy storage trends?
Exactly, yes. So as you see here on the pictures, so starting from tractors and going to any kind of utilities on the field, loading activities, the harvesting machines, spraying vehicles, smaller robots that are doing autonomous activities on the field, and but also to bigger transportation vehicles. And today, dominantly, the lithium-ion batteries, which is also the same technology that you see on the electric vehicles, is there. You would find also some machines operating with swappable battery systems to be more reduce the downtime and faster or replace the charging. Supercapacitor assisted system, which is more or less a niche, but also the hydrogen storage systems that are also looking or coming more and more. But predominantly, I would say lithium-ion battery, the same technology that's on the EV market, and this is standard technology at the moment. Now, the picture that we just saw earlier is showing the types of machines, now going on to classes of power classes. So starting from the lower segments, lower than 30 kilowatt, could be done fully electrically, looking at like smaller robots. These don't have a heavy weight. It could be fully electric. Then going from 30 to 70 as well. We were talking here about small tractors doing some limited daily activities or limited also operation time. Going to 70 to 100 kilowatt, there it could be maybe a hybrid system because as the machine is heavy, it needs more power, it needs to run for longer times. Starting from 100 kilowatt, it's fully hybrid. This is where you have big tractors, big transportation machines. Nevertheless, so you will still have a combination from these types of systems. As you said, the battery is the key components, and then the power class will determine if it could be run fully electric or a hybrid system that benefits from both worlds, the combustion engine and the electric.
So, Youssef, we're seeing a big growth in this market in particular, right?
Exactly. So the eCAV market will more than double by 2031. It's roughly 15% CAGR growth run by major factors or drivers. We have seen a big advancement in the battery technology, of course, driven by the EV market, and it's coming also here into the agriculture market. Strong push for sustainable farming, low emission farming, of course, government incentives, subsidies and regulations, and of course, rising fuel and maintenance costs so of diesel machinery and combustion engine in general. So these factors are pushing the market in that direction.
So, Youssef, what kind of trends are you seeing changing the future of eCAVs?
Looking at the trends, I mentioned it earlier, moving from 400 volt to 800 volt. This is a general trend on the EV market. You need to increase the power, then you have to go on higher voltage. This is as easy as it is. Then looking onto the hydraulic systems or the motors are going to replace the hydraulic systems. And these motors will be used maybe for small wheel motors, axle motors, or implement some drives to do some elements in the field. And these are multiple smaller electric motors. So not the same like the big motor that is running the machine, but is doing auxiliary activities. Then looking on the electrification, in general, this is the same thing as I was saying. So for steering, seeding, spraying, these are also moving away from hydraulic systems to electric systems. The sensor, very important component. We see more and more cameras inside the eCAV, more and more radars, lidars, position sensors in general to give this autonomous driving more or less. And this is a desired function in these machines to operate fully autonomously. And the machines are on the field doing what they have to do. And this comes together with the last point, which is the control and connectivity and remote connection and collection of data. You want to operate these things remotely, fully remote, have a bigger fleet, make algorithms and real-time analysis of what's going on. So all these trends, they will bring more components of semiconductors inside these machines. And that's why onsemi is a strong candidate for these types of applications.
What specific eCAV subsystems does onsemi directly target with its solutions?
Looking back on the block diagram that we showed earlier, this more extensive one, this one is, let's say, broken down onto the elements of interest to onsemi. So the tractor in the middle, then we look at the hard component, which is the battery. It needs an onboard chargers on the bottom left. It will need a traction inverter on the bottom that runs the motor, the electric motor. Then the sensors and the cameras we talked about, also a key component here. These things has to communicate between each other. So there's a wired communication inside the machine. We said also or talked about the hydraulic systems that are replaced by electric actuators. So this is also another component. It could be also the e-compressor and then the LED lighting in general for all the lights around the machine itself. So all these components are using on semiconductor products that are we going to show in the next slides.
Excellent. Okay, so Yusuf, why is the industry moving from 400 volt to 800 volt? And how does onsemi enable this transition?
Yes, great question. So 400 volt was the starting point for the EV, and then we noticed later that we need a higher voltage to charge faster these machines. So you have a shorter charging time, but also we can have higher voltage, higher current as the power is multiplying the current by the voltage at the end. If you have higher voltage, you have a higher power. And if you have heavier machines, you need a higher power to move these big machines and also to run for longer hours. onsemi offers technology up to 1200 volts. So looking at silicon carbide modules, IGBT modules, but also discrete parts. 1200 volt is necessary to run 800 volt systems. And if you look at these pictures, there are some discrete components on the left, and there are some modules. And these technologies also need gate drivers that you see in the bottom, galvanic isolated, because this high voltage is a danger for the humans. So we need to isolate all these voltages from the microcontrollers and from the low voltage stuff, but also from the human interface. And we can cover up to 90% of the bill of material of such a machine. So we will look more on specifically on each one of these components, but in general, the 800 volt is the future. We see it already on the EV, and it makes even more sense in the eCAV because of the high power requirement.
So, Yusuf, talk to me about the details of those power devices.
Yes, sure. So as we said earlier, the hard component is the battery, then the traction inverter that converts the DC to AC to operate the motor. We see in front of us one of these modules. We call them gel-filled module. It's an award winner module. It's an automotive grade module. It has a sintered die technology. It comes with a six-pack, and we see the topology on the bottom right. We see also the power class. So this module can incorporate IGBT technology or SiC, silicon carbide technology, but it is, of course, related to the power rating. As you go higher with the power, you will need or require less losses, and silicon carbide as a technology can switch higher, but also can have lower losses. And this is a better technology for higher power rating. But on the bottom left, you see also a typical specification of one of these modules, 900 volt, 620 ampere. So it's a really high current device that can run through the device. 1.7 milliohm is the lowest that you can see on this range. So this is a high-end module, high power module that you need to move such a big machine, right? So this is 600, and there is also even modules that go up to 1000 amps to operate these kind of big, heavy machines.
So, Yusuf, when should an engineer choose your half bridge silicon carbide module over a full six-pack.
Yes, so a half bridge is also another possibility for the engineers to choose. You see here the topology. This is the half bridge topology with the temperature sensor. A half bridge is a modular approach. So you can find also machines that don't have a three-phase motor. They have maybe six-phase motor or nine-phase motor or an open winding motor. There are types of motors, name it, yeah. And this topology, the half bridge, is a modular approach. So you can combine it as much as you want. This is a technology that is open. So the other module in the last slide, it was a three-phase, so it's kind of specific to that topology, but this one is more modular. It's flexible to be used in different topologies. Also, it has another packaging technology, what we call here transfer molded technology. You see it in the plastic and also with the topside cool copper orange material, and this is even a better technology in terms of power cycling and temperature cycling.
So, Youssef, what about your IGBT high power modules? Talk to me about those.
Yes, so IGBT is, let's say, the old technology or the still running technology before the SiC came over, but it still have a big use and still used today. We see here three types of modules. One of them, again, on the left is a half bridge in the Q-Dual package. In the middle is, again, a three-phase topology in the gel-filled module. And on the right, again, it is dual cooling kind of a transfer molded topology half bridge. And IGBTs are good for high power. They are also, in terms of cost, still a very good mature technology. The only limitation, again, is the switching frequency that cannot be very high. And also, when we go to much higher levels of power, then we can see the benefit on silicon carbide. But going back on the classes that we saw earlier on the machines, so 30 kilowatt and 50 kilowatt, all these classes of low, medium power range could be addressed by this type of IGBT modules. And then looking on the other side, on the discrete components, so not the modules, that we have the same again here. Discrete components are limited by the power. So here we see 100 amp, 150 amp. So these can be used in the auxiliary components, motors that don't have such a high power, so not in the main inverter. And here we split between silicon carbide MOSFET on the left, on the right, the IGBT. All of them here 1200 volt. We find on the bottom left also 650 volt. It could be also possible for 400 volt systems. But in general, you will find many components. You find on the top left, you see this SMD, D-square pack component, but also on the bottom right, you find a Q247 with 4 pins. So this is a through-hole component. So two types of mounting techniques at the end. It's the engineers, we offer the possibilities, and each one of these components have benefits that engineers can choose from.
So, Youssef, how does topside cooling transform thermal management and system reliability?
Yes, great question. So the topside cooling is coming more and more into focus. We see here two types of components here, what we call the T2 pack and the QD pack. In the past, the discrete component has to be mounted on the PCB, and then the heat goes through the PCB. And the PCB by nature is a thermal isolator. It's a bad thermal conductor. And then if we flip the die and we put the die on the top and then the cooling pad on the top, so we can then avoid the PCB and the heat will go straight to the heat sink. Of course, there will be some gel filler material in the between or some isolation, but it will have no PCB in between, and this will enhance the thermal performance by a great time. It will lower the operating temperature, will extend then the lifetime of the system in general. So these are very good packages. It needs, of course, a good mechanical design to have a tight tolerance to mount these devices directly to the heatsink. But once achieved, we can have factors by 2 or 3 of the thermal performance, and this is really a great thing. Also keeping the SMD approach, so these devices are all SMD, so it can be produced in an automated environment, so it offers plenty of benefits to the engineers.
Youssef, how does the Elite Power Simulator help engineers speed up their design to market time?
Engineers usually will go through the topology and then they will choose the devices. And then the first question is, will this device manage the requirements that I have from my customers, the current levels, the voltage levels? And the first step, of course, you before building a prototype that takes time and effort, and then you find out this is not the wrong device, you can simulate these things. And we have built a simulator, which is a very good simulator that gives you the ability to choose the topologies, the range of topologies for the inverter, for AC/DC, DC/DC conversion, for also multiple phase topologies, and then you can put in all the parameters from the devices. It supports other models, external models, so like PSpice, Symmetrics, EliteSiC, and so on. And then you type in all the inputs that you have from your system, from your client, and then you simulate those. You see at the end how many losses you have, how much temperature increase, and then you can calculate your safe margins and adjust, and you choose other devices. Of course, all the onsemi parts are featured in there, but you can also generate your own models and input your own device models and then simulate them. So it's a great start for simulating, getting a feeling about your design and improving, optimizing it to choose the right devices and the right topologies. Moving to the another discrete component, the JFET component, which is a special structure. It's not a MOSFET. At the end, needs a different gate driver. Actually, normally on device, what we see on the left, but also when put in cascode, it could be normally off device. So it's put in series with a low voltage MOSFET, so maybe a 30 volt MOSFET. It's then a 2-chip device, but then it has the benefits of both worlds, of the JFET and of the MOSFET. So now suddenly you can drive it like a MOSFET, but it has the very low RDS(on) that comes intrinsically with the JFET. It's better than the SiC MOSFET. And if we go even further to the right, to the SiC combo JFET, which has an additional gate pin, we call it the JFET gate pin, as you see on the picture, the JG pin, that gives you controllability of this device in terms of the turn on, DVDT, and turn off. And so the benefits on general of the JFET is the low RDS(on), and then putting in cascode or in combo makes it even easier to drive. And these devices, again, are discrete components. They are offered, as you see on the top side, called the package that we just talked about earlier. And it can be like in a battery switch, for example, where we need a very low RDS(on), but it could be also in kind of a DC-DC, AC-DC converter inside this eCAV machine.
Youssef, how can engineering teams use your double pulse testers to jumpstart hardware evaluation?
Yes, so we have built this double pulse tester to benchmark between MOSFETs and IGBTs. And this is the first step maybe for engineers. They have many suppliers and many components, and they want to test the dynamic parameters, but also the static parameters. And the double pulse tester is a standard tester usually for these kind of things. You can find this online. There is the eval board name in front of you, so it's you can order it and use it to evaluate. So this is kind of the next step after simulation. Then now you go and benchmark the MOSFETs and choose the right device. And then the third step, of course, would be putting it in your final PCB or application. But this is a good step between that saves time and speeds up development.
Okay, so on the low voltage side, what cooling and packaging innovations are you bringing to the table?
Exactly, yes. So we talked now a lot about the high voltage stuff, the 1200 volt, 650 volt. But on the low voltage stuff, we still have the standard battery, the 12 volt battery, 24 volt battery, or even the 48 volt. So most of the components will still run on these voltage levels. And then you will use the low voltage, medium voltage MOSFETs. Looking here, you can see the packages that we offer. So there will be 5x6, 3x3, 8x8, so 10x12. You will see dual cool, you will see source down, you will see topside cool. So all types of packages that offer thermal benefits, but also layout benefits. When we think about the source down package that gives you the flexibility to have a half bridge with less routing, with less inductances on your PCB, and all these things. We put an example of part numbers here for you with links that you can click on and see on onsemi. We have families of technologies, T10, T8, T6. So this is an evolution of trench technologies on the low voltage side. Talking about MOSFETs in general, it has to be paired with the gate drivers. You see in front of you, every MOSFET needs a driver, and a driver especially in the high voltage applications, needs to be isolated. It could be a single channel with many features. It needs a strong current and a big isolation to run these devices. But also it could be a smaller the package, just one feature. So we have a range of types here that you see in front of you. It can be used for IGBT or SiC, as we said. So it can be SU16 package or SU8, depending on the isolation requirement you have. It's 3 kilovolt or 5 kilovolt or more. And we have put a selection tool for you, so it's also accessible here, and it gives you the right gate driver for the right semiconductor switch. Again, here for the page, we see the table. There are some gate drivers that are paired with the low voltage FETs, with silicon carbide FETs, with IGBTs, but also with silicon carbide modules.
All right, so Youssef, specifically within the vision aspects of these eCAVs, what kind of components are you seeing being used today?
Yes, so we have image sensors inside onsemi. This is a big portfolio and it's a long history. We offer those in the industrial market, in the automotive market, and also for the eCAV, this is a big application. So these sensors, they give you the ability to capture the environment with a camera. This camera has to capture maybe a higher resolution. It has to have a low power consumption. It has to have a more dynamic range to capture low light, high light in the dark during the day, wide spectral sensitivity. So there are families for that. In marketing names, we call them Python, Hyperlux, Sphere, XGS. There is, of course, specifications for that. So, but we have the right camera for each need. We have from 1 megapixel to 45. There are rolling shutter and global shutter technologies. So the global shutter will be more adequate for moving objects, roll and shutter if you capture a static object, and so on. The camera is a big portfolio, as I said, and there is for each need, you will find the right solution. Of course, on the bottom of that, you will see the power supply that is needed. So it could be an LDO or PIMIC to provide a stable voltage level and a stable camera picture. And that is needed on the supply side. That's why you have to choose the right LDO with a very low PSSR, for example, and so on.
All right, so Youssef, give me some more information about those global shutter image sensors.
Yes, global shutter is that the camera is taking a picture at one element, so not by line, but just a single shot. And this gives the benefit to capture while capturing a moving element, then the camera will not have artifacts inside the picture. And here we will find different families or subfamilies depending. If you look at Python, this is a rich family with many options. You will see some examples on the bottom with 1.3 megapixel, 5 or 25. All these are production. There are some cameras, the XGS are superior low light cameras, and the Hyperlux, there will be the highest resolution as you see here. There will be also some with smallest format or high speed. So many subfamilies that cover different features and different requirements. But at the end, you will find the right solution for your need. On the next page, we see the rolling shutter, which is the opposite of the global shutter. Then here we talk about capturing a picture line by line. This makes the camera concept or the sensor itself a little simpler inside and could be also cheaper, but it will not be very perfect for moving objects. It will be for kind of slow object or static objects. And then for these customers that focus more on the low power, they don't need the highest resolution and the biggest features, then you will find here the right camera for you. On the right side, you will find the Sphere camera, which is a shortwave infrared camera, which is an infrared camera at the end. And then this is a special application here if you want to look beside the visible area.
So, why is electric actuation replacing traditional hydraulics so rapidly in modern farming?
Yes, great question. So the hydraulic actuators are, as the name says, hydraulic. So they are based on oil and they will have higher maintenance, some leaks. They are not very precise and they cause some vibration. And in terms of reliability, they have lower lifetime. And the trend is to remove those and replace by electric actuators that have higher efficiency, that can be controlled digitally. that are scalable and they need no maintenance and no oil, no nothing. So pure electric, clean energy. So speak about brushed or brushless motors. We can find here on the bottom the drivers that you can use, or also low voltage MOSFETs with topside cool technology that are already in use, by the way, in electric cars and passenger cars, and that could be here a good expansion in this eCAV environment.
So, Youssef, how does 10 base T1S Ethernet simplify in vehicle wiring and eliminate these heavy switches?
This is a new technology. 10 base stands for 10 megabit. It is a bus systems. It's comparable to CAN and LIN, so multi-drop. So you can connect many devices on one single bus. It has up to 10 megabit, and this gives the ability to connect devices that were not accessible in the past with IP address and Ethernet environment on the edge. And this is a great advantage. It will save cables and heavy cable and weight inside the cars, but also in the eCAV. It is benefiting also from the long history and reputation of Ethernet itself. So it's established technology, established platform and protocol. And then if we bring this even inside the car and the eCAV, that's an additional benefit here in terms of controllability, connectivity, and so on. Then looking onto the LED portfolio, we said earlier that the machine needs lights on the front lighting, the back lighting, and these are typically LEDs, and the LEDs needs to be driven by a driver, typically coming from the 24-volt battery, and then these drivers needs to boost the voltage to have higher count of LEDs in series, and this will need, for example, an H-bridge boost converter or buck converter. You can also have kind of pixel on the right. So you have for each LED switch that controls it and detects when it's short and open and it's failing and so on. This is an advanced, of course, kind of LED driver, but we offer the full range from simple to more complex LED drivers for your needs. So in total and general, so we talked about all the key components. There are also other components from onsemi that can fit inside here. We call them complementary onsemi parts. Name it, so op amps, current sensing, level translator, other sensing components, ESD protection, memory, digital isolation, and also wired transceivers like CAN and LIN. The BOM itself is composed of all these components together at the end.
All right. So, Youssef, overall, what do you think onsemi brings to the table when it comes to these kinds of designs?
Yes, so as these eCAVs, machines, and electric vehicles are implementing more and more electric and semiconductor components, onsemi has all types of components that fit in there, starting from the key components that are these modules that run the electric motors using types of technology like IGBT and SiC, and the gate drivers that needs there, but also the sensors, the image sensors, to capture the elements and the environment, and then the DC-DC power supply components, the communication, as we talked on the Ethernet and so on. It's a high content, yeah, a high onsemi content, and up to 121 components, yeah, on one PCB. This brings to your attention that this is a focus market and application for onsemi. We have the experts that helps you choose the right components and solve your technical issues.
All right. So, Youssef, if my audience wants more information, what kind of supporting assets does onsemi offer to help them on their way?
We have multiple tools online, technical and marketing tools, and also design tools. So you see in front of you, we have also other videos like this one that go even deeper on the technical aspects of the components, explain the devices. We have application notes. We have solution guides that show you also the block diagrams of the applications. On the bottom, you see the design tools. We talked about one of them, which is the power simulator, but there are also other tools that give you simulation for the power supply, for example, or the gate driver, or the current sensing design tool. But then also the product pages themselves for each and one of the components. So you will find the filter tools. You can filter and choose the device based on the package, the voltage, and so on. And you will find also the complementary components for each of them. So we try to collect all of these on one page so you can click them find them and find the right solution and right support and answers for your questions.
Fantastic. Well, Youssef, I think that's all I have time for today. Thank you so much for joining me.
Thanks for having me.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from onsemi. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.